Um, so, hi everyone. Thank you for coming. Just a quick survey before I start. How many of you are comfortable with Python code? See Python code? No, majority. And how many of you had encountered imbalanced datasets before? Most of you. So let's start. So my name is Zehori. I'm a data scientist at BigaBid, and you can find me at all these places. So let's just go through the agenda for today. What we're going to talk about. So basically, we're going to define what is imbalanced data first. Secondly, we're going to talk about the accuracy paradox, on which Michael had touched in his previous talk. And we're going to see why accuracy isn't such a good metric. We're going to propose some alternative performance matrix to accuracy. And then we're actually, this part, the last 3 bullets are actually going to be the tools that I hope to provide you guys to actually tackle the problem hands-on. So we're going to talk about the ratio parameter, which is a pretty powerful tool if you work with scikit-learn. We're going to talk about some resampling methods, which involve mainly manipulating the data, and that's going to be the bulk of the talk today. And we're going to finally mention some ensemble methods, which mean this is a different tactic to for the actual algorithm that we're going to use. So let's, and then this is fairly technical, so I will try to make it brief for you guys to, so you'll be cool with it. All right, so let's start. So what's imbalanced data? So basically imbalanced data is a case in which we have a classification. It doesn't have to be a binary classification. It doesn't have to be 0 or 1. It can be you can have multiple classes, like in the iris data set, if you guys are familiar with it. But basically, for this talk, we're going to focus on binary classification, 0s and 1s. So imbalanced data means that we have a large chunk of points, of data points, which are basically, they're the negative samples. They're the ones who haven't clicked. They're the ones who do not have cancer, and they're the bank transactions who are not fraudulent. I'm going to stick with the fraudulent bank transactions for this talk just to make it, just so we'll be on the same page. So the distribution is not uniform, and usually the minority class is the interesting one. We really care about the minority class because, I mean, misclassifying a bank transaction, a non-fraudulent bank transaction as fraudulent, oh, well, it's going to cost us $1, right? It's going to go through the analyst, and he's going to look at it for just 5 more minutes, and he's going to classify it as, that's fine. But misclassifying a fraudulent one, that's going to cost us a lot of money, right? So $3,000 for the sake of this conversation. So where can we find imbalanced data? So we have a doctor from South Park. Basically, we can find it in medicine everywhere because it's a fair assumption to say most people are healthy. Right? So data sets that they deal with there is basically they try to classify types of cancer from images, stuff like that. Most of the positive examples, positive examples are the minority class there. Bank transactions, just fraud in general. Most cases aren't fraud. Most cases are just fine. And we can see it in web ads, in click-through rate, CTR, which is a great segue to kind of present you guys with us, with BigaBid. So who are we and what do we do? So other than providing the delicious pizza that you guys are eating, what we do is we work with high-powered brands such as Uber, Get Taxi, Miniclip. These are app developers. And what we do basically is we use powerful machine learning techniques and AI that is proprietary to help them find their audiences. Say they want to infiltrate a new market. Say they just want to just get some more customers to download their apps. So we help them find those people and we help them get them. So just the stack, this is why I asked about Python earlier. So just the stack, you're going to be pretty familiar with it. It's pandas, numpy, matplotlib, and seaborn. If you guys don't know about seaborn, it's a really powerful plotting library you can use. We're going to use collections, just a Python thing. We're going to use scikit-learn to generate some data, and it's going to provide us with the model. And we're going to use imblearn, which is imbalanced learn, to do the resampling part of the talk. So let's dive right in. What's the accuracy paradox? So basically, to make this more concrete, we're going to generate some data. So just line by line, we're going to go. I'm going to make classification. It's a scikit-learn function that generates some synthetic data, and we're going to generate 5,000 examples. And samples, that's a parameter. We're going to use the class separation. It means how separated the two classes are going to be. So it's going to be 1.3. That's pretty arbitrary. Weights is the most important thing because we're talking about imbalanced data. So the majority class is going to consist of 95% of the data, and the minority class is going to be 5%. Then we're going to decompose it into just a plottable two-dimension data set and go from there. We're going to name them PC1 and PC2. So this is get comfortable with this data set. We're gonna have it on the screen for some time now. So what basically, I mean, we've generated this data set. So what's our goal actually here? What do we want to do? As data scientists in this scenario, in the classification environment, what we really want to do is we want to create a decision boundary. What's a decision boundary? Well, basically it's a line. In our case, it's going to be a straight line because we're going to use a linear decision boundary, and the line has to separate the two classes. I mean, and for us as humans, it's pretty. I mean, just looking at this, you kind of know where you want your straight line to be, right? I've given you guys some examples. This is a decision tree. This is a neural network. There's all types of decision boundary, but we're going to focus on the straight line one. This is a function that takes a model and it takes our data, takes a sampler, it plots the decision boundary, and it reports some scores. So we just took our data, just vanilla, put it in the scikit-learn, logistic regression, no sampler, and we got this. We got a 94% accuracy, which is pretty good, right? I mean, you can go to the bank with 94% accuracy, but we can do even better. We can get a 95% accuracy just by returning false from a function called my classifier is better than yours. It's better than yours. I'm just kidding. So just to make this more concrete, what did we do? We just returned false all the time. Basically, we just said, we had a classifier that just said, it's not fraudulent all the time. So the cost, it only missed 5% of the samples, but we're not particularly good at fraud detection if we just say everything is not fraud, right? So just to make this more concrete, just a little survey again. Sorry, you're so active. Which decision boundary would you guys prefer? A or B? A, right? A has somewhat of a predictive power. It says something meaningful about the data, right? B just returns negative all the time, right? Because left of the line it's negative, right of the line it's positive. But you're going to be surprised that B has a higher accuracy rate than A, right? Because A misclassifies 4 points and B only misclassifies 2. And this is why accuracy is not a good measure. Luckily, we're here to talk about alternative performance matrices. So in order to talk about this, the segue, I mean, this is the bread and butter for classification. This is the confusion matrix. Every guy in this room, guy or girl, has to be familiar with this. So basically what we have here is it's a 2x2 matrix, and every data point fits in exactly 1 square. This is the confusion matrix from our classifier, just so you'll have a reference. And basically what we do here, when we talk about accuracy, we look at the true positive and the true negative rate. That means the positive labels that were actually classified as positive and the negative labels that were actually classified as negative. And we divide them by the whole thing, and that's how we get the accuracy rate. Now we're going to look at something else, a ratio, which captures the type of errors that we do. We're going to look at specificity, which basically means taken from the negative sample. We're going to take whatever is actually negative and divide it by all the negatives. And we're going to talk about sensitivity, which does the same thing for the positives. It takes the positive and divides it by all the positives. I'm not going to go into too much detail here, but these two can be plotted against each other and create the ROC curve, and we can calculate the area under the curve and get the AUC metric, which is a better. I mean, I just want to emphasize one point: you can never have a classifier that fools you like it does with accuracy, with sensitivity and specificity. And why is that? Because once you take the specificity all the way up, you lose sensitivity, and vice versa. You can never have both. I mean, if you have both, then you have a perfect classifier, which in our case is not possible, as you see. So let's predict this. Let's talk about the scores from our naive classifier. So the AUC goes between 0.5 and 1, so we get a pretty poor 0.56, and the geometric mean is referred to the geometric mean between the sensitivity and the specificity. It's a nice kind of compact way to talk about both. So the ratio parameter. Now we're actually getting into the meat of the conversation, the reason why you guys are here probably. This is a way to deal with imbalanced data. So when talking about the ratio parameter, we're basically talking about modifying the loss function, because all machine learning really is defining a loss function and minimizing it over some data. That's basically what we're doing. I mean, generally. In classification, you define some loss function and you go ahead and you minimize it. With the ratio parameter, what we do is, behind this classification task, if you're talking about fraud and not fraud, there's some type of hidden business logic. If misclassifying something that's fraudulent as non-fraudulent costs us $3,000, and misclassifying something that isn't fraudulent as fraudulent costs us only $1, then the ratio should be 3,000 to 1, right? Because making a mistake, we want to tell the classifier explicitly. We're going to tell them that making a mistake on a $3,000 is 3,000 times as costly as making it on a $1. So basically what we did here is we used the class weights, and here I just used the inverse proportion of the class weights, and we can see that the AUC had skyrocketed into 0.814, and the geometric mean, they're pretty correlated. The geometric mean is 0.812. So just by doing this simple trick, just reweighting the loss function, we got a pretty good classifier. This is the bulk of the talk. I'm going to talk about, we first talked about manipulating the loss function, now we're going to talk about manipulating the actual data. So just a quick reminder for you guys what's random oversampling and random undersampling. So basically in random oversampling, what we do, did you see the beautiful animation Uli made for me? In random oversampling, basically what you do is you take the minority data points and you just multiply them. You just sample them over and over again until your data set is balanced. In random undersampling, what you do is, you guessed it, you randomly select from the majority class, and you take the samples out until the data set is balanced. What's the problem? Random undersampling, you see this outlier over here? It got sampled, it may not get sampled. Data set decision boundary can vary by quite a bit. Oversampling really causes overfitting. If you guys are familiar with the concept of overfitting, basically what you do is you create many instances on the same instance. So you duplicate the points. So the classifier would mistakenly think that you really sampled a lot of points from that specific region. So let's just report the score. So the AUC is a 0.819 and the AUC is 0.816. As you can see on our data, it does a pretty good job. Now we're going to move to some smarter ways of doing things, because random sampling can only take you so far. So cluster sample rates. Basically, what it does is it's an undersampling method that tackles the issue of what I told you before about the outlier that might not get sampled. So basically what you want to do is you want to make sure that the entire space is the entire space that the majority class lives in is represented in your data. You don't want to leave it to chance to say there's an entire region of my data that I haven't sampled from, so my classifier has no idea that there's a majority point there. So basically what you do is you avoid information loss. As you can see, the majority class is well scattered. It uses the k-means algorithm, and it just uses the centroids of the k-mean algorithm as majority class centers, basically data points. And as you can see, the data is balanced. It started with 3,150 to 200, now it's 200 both ways. Matrix got down a bit, but they're still in the okay region. One-sided selection, I think I'm a bit long on time, so I think I'm going to skip this one. Smooth algorithm. This is basically a smart way to oversample. What you do is you avoid the overfitting I was referring to earlier in the random oversample by basically taking the minority points, right? And then you pick their nearest neighbors here, and you draw a line between them and the nearest neighbors. There's some subtlety about what's the radius, how many nearest neighbors, how do you sample from them. But basically, the main idea you need to know is you draw a line between every point and its nearest neighbors, and you synthetically inject new data points on that line. So now our data points do not overlap. So they're pretty much, they cover the entire minority class region, and it looks kind of like this. So in our case, it's a mess, but it works. You see the metric, it works pretty well. And this is a really powerful method. One thing to notice, this is computationally expensive. So when using this technique, bear in mind that it's going to be quite expensive if you have a lot of minority examples. Just a brief, I'll talk about Tomac links, which is going to be a great segue to Smooth plus Tomac links, which is our next thing. So Tomac links, basically, what you need to know about them is that there are 2 points. They are each other's nearest neighbor, but they do not belong to the same class. Basically, what you do with Tomac links, you remove them, and you make the data a lot more separable. So when combined with Smooth, that is actually a technique we've been experimenting with it at BigaBid, and we got great results with it. So basically what you do is is you perform smooth on the data, and then you remove the Tomac links. And as you can see, the separation between the two classes becomes really clear when you do that. So this is overall the best metric we got. This is 0.82 in the geometric and the AUC. We're going to move away from resampling for a second. We're going to talk about ensemble methods, which is our third and last topic. And this topic involves, so we talked briefly about modifying the loss function and penalizing it. And we talked a little about resampling methods, and we've mentioned some. So ensemble methods, it really boils down to the modeling approach. So basically what you do, and I'm going to mention easy ensemble, there are a few more. So basically what you do here is you take the majority class and you sample from it, you randomly sample from it. And you teach and you train an AdaBoost classifier on the sample and the entire minority class. And what you do, you iterate over it. And what you end up with are a bunch of classifiers, N classifiers, that you got to combine later to create your classification. So basically this is an ensemble of classifiers that vote, and you end up with your classification. This is an extremely powerful method to use. And I don't have the score to report for it, but it is really it is something you got to bear in mind. So some more techniques that I haven't gone through are balanced cascade for ensemble. This is basically the difference is that the sampling is not random. You select, you make sure that the points you've made a mistake on stay on the data. DB smooth involves DB scan. ANS is parameter free. If you guys, you can just throw some data at it and see what comes out. So just to summarize, this is the last slide. We've been through ratio parameter. We've tweaked the loss function. We went and the ratio parameter. This is really important. You got to know. You got to do your homework. I mean, you got to know how much misclassification costs you. I mean, if making a mistake, like the 3001 thing, so put this ratio in. Let the classifier know, because you basically, the more information, the better. Oh, I mean, in data science, I mean, we're all about information. Just convey that piece of information to the classifier, help it make a great decision. Over-undersampling, so we talked about various methods. You manipulate the data, and by which you get a pretty good AUC and other scores. In the spirit of the no free lunch theorem, there is no one way that works. Just you now have a set of tools to bear in mind when coming to think of a classification problem of this sort. Just try them out, play with it. I mean, in some cases we have. In our case, we only have one cluster of minority class. We can have 3, 4 clusters, right? So different resampling methods can perform better or worse in different conditions. And the ensemble method, this is a modeling approach. You got to take in consideration if you can support it in production. There are a lot of considerations to think about, but it's a really powerful approach, and you can combine the classifiers in various ways. Thank you guys very much. Any questions? No questions. Thank you then.